My name's Alistair Scott. I'm a past president of the British Interplanetary Society, and now I just run the events, or run the events committee, and they do all the work for me. What I'd like to say is welcome to the BIS. Some of you have never been here before. Please ask to look around if you want to, and we'll show you where everything is. Now, for those that don't know the British Interplanetary Society, please look at our website, bis-space.com, and you'll find out all about us. Now, we're very pleased to have, well, let's say an unusual talk tonight, I hope, which is going to talk about the philosophy of Starship. And I'd like to just introduce Kelvin Long, who's going to come and tell us all about it. Kelvin is a physicist and an aerospace engineer, and an author in his spare time, if he's got any. And most important, though, he's a fellow of the British Interplanetary Society and was the chief editor of our journal, the British Interplanetary Society Journal, JBIS. So he's actually got tremendous experience, but actually more than that, he actually was the BIS project leader on the Icarus program, and then later formed Icarus Interstellar, which is a US-based company, and also has gone on to form a company called Interstellar Studies. So he's got tremendous experience of interstellar travel and getting us up there. So I'm hoping we're going to hear all about it tonight. Over to you, Kelvin.
Thank you, Alistair. Let's make sure this doesn't fall off. Okay, so let me get some idea, first of all, who's never been here before? Just to get some idea. So, okay. So when I wrote the slides, I sort of marketed it more towards the BIS, so I make sure I just assume most people sort of knew me because I've been here quite a lot in the past. So I make sure I add in some introductory nuggets to sort of explain what this is about. So who's interested in interstellar spaceflight? Okay, that's amazing. There you go. So that's really good to see. So can anyone guess what the spaceship is on the front cover of this slide? Okay.
It's the fictional spaceship from the movie Passengers.
Okay, do you know what it's called?
No, actually.
Anyone? This is your test. Anyone have a guess? Come on, John, you know.
I've forgotten, sadly.
Oh, gosh. The Avalon. Is that Terry? Right, the Avalon, okay. Anyone seen Passengers? It's a good film. It's worth watching, okay. So, how do we think this works? Any idea?
Stellar Ramjet.
Micro black hole.
So, lots of ideas. It's good. Just give me an idea of sort of some of the thoughts. Yep.
Sublight sleeper ship.
Sublight sleeper ship, okay. So in the film it actually goes 50% of the speed of light, and it's actually based on a sycamore seed. You know, those little helicopter things you drop from the trees, the design. So it's rather artistic. You can see the exhaust coming out the back, and you can see right at the front there's this little tiny illuminated light. We're not quite sure what that is, but I suspect it's something to do with ionizing the interstellar hydrogen or interstellar medium, so that you can create some plasma which you can then use as fuel, because you don't see big fuel tanks on it. So, so that's the first introduction to starships. As Alistair mentioned, so I was involved with, my introduction to Interstellar was actually through warp drive theory. That's where I first got interested in it, through general relativity. Then I got more practical into Daedalus and Project Icarus. Who's not heard of Daedalus? Let's see who's, don't be shy, put your hand up, right, so I'll make sure I introduce Daedalus. That's the flagship model for the BIS. Where is the model, Alistair? It's in there. Make sure you have a look at that before you leave today. There's a big model in there, which the builder is actually sitting at the back, Terry. And so I then went on to found Project Icarus, which was a design effort to design a starship on paper, and also co-founded a company in the United States called Icarus Interstellar, which is still going strong, and one in the UK called Initiative for Interstellar Studies, which also has a US arm called the Institute for Interstellar Studies, and several of the members of that are here today, such as John. And my latest venture is this organisation called the Interstellar Research Centre, which is a private, for-profit company, but it's primarily focused on interstellar, but other questions as well. So I have a little obsession, and for anyone that's ever read any ancient spiritual mythology, here's a quote from the Buddha: "Your purpose in life is to find your purpose and give your whole heart and soul to it." So for me, it was starships. I sort of felt I had a calling to design starships. And that fell on my lap around 2007, but I had some of the ideas for that much earlier. And really what was the inspiration for that was the work done by the British Interplanetary Society, particularly in the 1970s, and some of the people from that original team are here, such as the president, Jerry Webb, Alan Bond, Anthony Martin, Bob Parkinson, some really great pioneers in the field. And I believe what I'm going to do is take you on a journey through some of that today. So I fell into this field, but actually after spending 12 years building these organizations and companies, I realized that the Starship is very complicated. It's not just about the technology. I remember we had a World Ship symposium 2 days in here a few years back, and Jerry was there, and it was dominated by social and political discussions. You know, if you could build a world ship and you throw lots of people off to the stars on a journey of 1,000 years, it's actually not the technology that's the problem, it's whether people can get on and what sort of social structure and governance structure is required to make it successful. So I began to realize with my own endeavors that actually you need to have a more broader understanding. So when I created this Interstellar Research Center, I actually set it 7 research questions that I want to sort of think about addressing. One of those is interstellar travel, as you can see. Can we get to the stars? But I'm also interested in survival of the human species. Worried about things such as asteroid threats and so forth. Of course, at the moment, we're in a state where we potentially have a disease epidemic that could arise. That's a bit of a worry. The nature of Homo sapiens, when you look into the history of humankind, it's quite clear that we don't have a very good understanding for the origin of Homo sapiens, so and how they're connected to our cousin species such as Neanderthals and others. So I'm interested in that. And also, is there intelligent life in the universe? Fundamental physics such as why can't we unify general relativity and quantum mechanics? And then what is reality? What is this world we live in, which we call the universe, and then consciousness. So what I'm essentially interested in is what is the role of a human being, us, in the cosmos? What is the connection to us, to the cosmos? If you're a materialist, then you believe that connection is clearly explained through evolutionary biology. If you're an idealist, perhaps you have a different view, that you believe consciousness is all pervasive, and perhaps it precedes materiality. So there's all those kind of ideas and perspectives which go into it. And I think that you really need to have a better understanding for some of these issues if you want to build a sustainable Starship culture before you can go out into the universe and explore the heavens, as it were. So we actually have a building in Gloucestershire. This is in the village of Charfield. 6,500 square feet building. It's similar to this one. And we do events. David Baker, who's the editor of Spaceflight, came and gave a talk only a couple of months ago. We have a small space downstairs, which we call the Bridge. So if anyone wants to come and listen to one of our talks, you're most welcome to. That's in Gloucestershire, as I say. We were the home for the Initiative for Interstellar Studies for a couple of years. They had a lot of really good programs and projects, and they're still going strong. We're still talking to them. So a little bit of advertising. I think this is very helpful to me. So I've got a couple of things coming out. This is a book which comes out at the end of March. It's pretty much done. Just making some final touches. What it is, I took a lot of blog articles from the past and essays that I've written. I've turned it into a book. So I've thrown them together. So a lot of the topics I'm going to talk about today are kind of covered in this book. So this will be out in March. And you can find it on Amazon. So if you just look on Amazon, you'll see the book. And also a couple of monographs to advertise. Mathematical models of solar wind. That's currently published. That's also available on lulu.com at the moment. And the other two, which one is Foundations of Interstellar Flight, so if you want to get into the basis of the field. And the other one is a project I have called the Yak Palu Initiative, which is an initiative to build a stone artifact that can survive at least 100,000 years. So the idea is you take something and you chisel on it the knowledge of human society from architecture to biology to physics, so that in thousands of years from now, if humankind society declined and someone dug it up, it could help them to reboot society. So anyway, these are 3 of the books, and they're actually paintings by me on the front covers. I got into painting 2 years ago. I'm not particularly good, but I really enjoy it. So inspired by a lot of my artist friends. You're going to see a lot of art today. So what I've tried to do is minimize text. There's a few slides with text on, and just give you lots of images. Okay, so there's going to be a lot of eye candy, so I hope you enjoy the pictures. So can anyone recognize this? Not a BIS member, please. Anyone who's a non-BIS member, can you recognize this?
Viking?
Similar. Any others? Any other ideas? It begins with V.
Yeah.
No BIS members allowed to. Come on. Okay, this is the Voyager probe. Launched in 1977. There's 2 of them, Voyager 1 and Voyager 2, and they were launched out into the solar system, and they are currently beyond 100 AU, about 130, 140 AU. So an AU is the mean distance between the Sun and the Earth, okay? So that's what we call an astronomical unit. So the Voyager probes is the best we've done to date in terms of a Starship. There is, the best we've done in terms of a crewed starship is the ISS, because it's an orbiting structure 400 kilometers above the Earth, about 450 tons of mass, and it had a permanent presence pretty much for 20 years. So if you were to put big engines on the back of that and push it off into space, it's kind of like a starship. There's various reasons that wouldn't work, but you get the idea, okay? So we're emerging as an interstellar society. We're trying to get out into the interplanetary medium, and eventually can we get to the stars? And this is the things I want to address today. So this is actually the Voyager spacecraft replica at JPL in Pasadena. And this is a picture of me standing next to it for scale, because I think it's really important to have that scale. And you can see it's really, really big. Is there a laser pointer here? Can't see a laser pointer. Anyway, so what you can see is the big antenna on top. That's the communications antenna. It's the main high gain antenna. And you can see right at the back here, this is the plutonium RTG. This is what powers it. And you can see the plaque. That's a message to any intelligent extraterrestrials that will find it. So this was sent out in 1977. Carl Sagan, the American astronomer, was very much involved in that. And those are still transmitting. They will be transmitting probably until around 2025. After that, there's no spacecraft that are at that distance transmitting. New Horizons is out there. That's gone past Pluto, and that's now starting to think about its interstellar mission. Interstellar means different to me. Interstellar means going to the stars to me. I would call that an interstellar precursor mission, because it's going outside the solar system, outside the solar heliosphere, which surrounds our solar system, but it's still not as far as the stars. The stars are very far away. The nearest is 4.3 light years away, 270,000 AU. Remember, an AU is distance from the sun to the Earth. So it's a really long distance, okay? So these travel at something like 17 kilometers per second. To get to the stars in around 100 years, you need to be traveling much faster than that, like 10,000 kilometers per second-ish of order. So much faster. So for any science fiction fans in the room, here's some example of some of the books. Now, interstellar flight was not really a field. If you go back in the day, it was more of a hobby interest, you know. But there were lots of authors who were writing books, dreaming about people traveling to the stars, from Robert Heinlein to Arthur C. Clarke, who was one of the founders of this society, and came to this building when he was alive, and I met Arthur, and Carl Sagan and others, you know, and I'll be touching on some of these technologies, and that's what I'm interested in, is the technology that goes into these particular concepts. So let's have a look at some of these. These are some of the books that have been published. There's actually a few more. The earliest I found is 1965, James Strong. It's a really good book. And all of these books have really been people trying to write a synopsis of the field. What does it take to go to the stars? How could we get there? Who's going to make the journey? All those sorts of discussions. And it's really interesting to get into that library and understand it. So what I've done is I'm going to take you on a bit of a journey of interstellar studies in terms of the particularly propulsion technology. That's what I want to focus on mainly today. Starships are much more than propulsion, of course. You've got the payload, you've got the power systems, the heat radiators. You'll see a lot of this in some of the slides. You've got the crew, you know, closed life support systems if you want to have people on board. The propellant, fuel. So there's a lot to a starship, navigation and so forth. But what I want to focus on mainly propulsion, because that's my particular interest. And it is BIS centric, because this is the BIS. And the BIS has been very much involved in this journey. I've always called the BIS the flag bearers of interstellar for many years. Until probably the last 10 years or so, you've seen a lot of organizations emerging to do with interstellar flight. So I've split it up into 3 eras. The first is what I call the Foundations Age, which begins from about 1950 up to about 1973. So Eugene Sanger was one of the first people to write about interstellar. I've never actually read his books and his papers, so I'm trying to get hold of those at the moment. But one of the things he talked about was, how could we build an engine that could take us all the way to the stars? And he talked about anti-electrons, so as antimatter. But he didn't know how you can actually do it in practice. And he also, at the time, no one knew you can get antiprotons. So antimatter is similar to normal matter, but it has different opposite properties. One of the other founders of the field was Les Shepard, and he was also one of the founders of this society. And he wrote one of the first papers, and I only read it this morning again, because I've not read it for a few years, in 1952. And there's two particular paragraphs I thought were so good that it was worth quoting them. There must be many who cannot derive spiritual satisfaction from the picture of mankind spending its whole existence in one single infinitesimal planet with no contact with other species who made people countless other worlds of the universe. So he had a very optimistic view. But I love this bit. The notion that the impossibility of velocities greater than c places any serious restriction upon interstellar communication is based upon a rather narrow outlook. It is true that if we think in terms of interstellar vacations, business trips to Capella and interstellar warfare, a certain inconvenience would be encountered. I thought that was quite funny. But these are a few minor features, and taking the broad view of things, the fact that it may take many years to go from one system to another is no great restriction. So when you look at his paper, he was looking at 5,000 to 10,000 kilometers per second exhaust velocities, traveling sort of centuries to the nearest stars, up to about 1,000 years. He thought that anything less than 1,000 years wasn't credible, there's no point trying. But he does talk about what we call world ships a little bit, and the idea of sending lots of people. It's a really great paper, and as I say, I only read it again this morning. Now, when we look at what it takes to get to the stars, we have to look at the energy, right? Because it takes energy to do anything. So you can look at chemical. Now, the units we tend to use is, you've heard of joules, right? And you've probably heard of that unit at least in kilograms, which is mass. So we use something called joules per kilogram. It's an energy per mass. And if you look at chemical, you're looking at something like 13 megajoules per kilogram. And if you look at fission, and you can then start to understand why people are interested in nuclear. It's 82 million megajoules per kilo, okay? And you go to fusion, something like a D-helium-3 reaction, you get to 347 million megajoules per kilogram. So the energy is so much more. And then you can combine some of these, or you can even go to antimatter, catalyzed fusion, I'll talk a bit about that. And then full antimatter, which is a full annihilation reaction, taking you potentially close to the speed of light. Which is 90 billion megajoules per kilogram. Okay, so you can see the enormous differences of more energy, we call it bang for buck. The more bang for buck you have, the faster you're going to go. What you want to do is minimize the transit time. You don't want to be spending too long traveling to the stars unless you're on, a huge world ship, which is essentially like a planetary ecology. So, and then you can look at alternative ideas, these are speculative, such as mining the quantum vacuum, propellantless solutions, like the idea of not carrying fuel on board, but actually beaming some energy to the spacecraft, which pushes it along. So what we tend to do is we look at nuclear reactions, and these are, when you look at people trying to build nuclear fusion reactions on Earth, for example, they tend to be playing around with, can we annihilate deuterium and tritium together to produce helium-4 and a neutron. So like the ITER in France or the National Initiative Facility in San Francisco, that's essentially what they're trying to do. They're trying to produce something which is giving more energy out than they put into it. Trying to produce the energy of the sun, and that would solve all of our energy needs if we can make it work. All the energy needs of the planet could be solved by that. So, but the problem is, neutrons are radiative. Okay, and also they have neutral charge, so you can't do much for them from a propulsion perspective. You want to have something with charge so you can magnetically direct it. So what we like is this particular one, deuterium and helium-3, because this produces a helium-4 particle, which is charged, and a proton, which is also charged. And the problem is the abundance of helium-3 is pretty scarce, which is why we talk about going to the gas giants to get it. Deuterium is much more plentiful. There's other reactions we can look at, such as lithium and neutrons and others, proton-boron reactions. So some of the first papers on fusion, such as Lawson in 1957, is where the fusion field started to really take off. And from propulsion, we always think, how could we take those ideas? So now we get to Project Orion. So you've all heard of the Manhattan Project. Yes, which is, people have different opinions about it. But during the Manhattan Project, or shortly after, two of the physicists that worked on that, Stanisław Ulam and Cornelius Everett, they actually started to think about, well, can we use this technology of essentially a bomb to propel a spacecraft? And that's the origins of the idea of Project Orion. And it was actually a project from 1957 to 1965 under the United States Air Force, General Dynamics. They actually tried to design and build test beds for a bomb-powered spacecraft. So this thing could actually take off from the Earth, and that's where it was controversial, because you're detonating bombs on the Earth, just like out in the desert. But potentially it's radiative. It involves fission bombs, it's radiative, so that's not good for the atmosphere, because you could spread it. Another way you could use it is actually just build it up in space and then launch it in space, because there's lots of radiation in space anyway, particularly if you go out to the gas giants like Jupiter. As long as you're outside the Van Allen radiation belts, the Earth won't be affected at all. And in principle, you could use this technology. So what actually happens is, this is where the payload would be, and there would be a crew on board. And these are the propellant tanks. And here, these are called shock absorbers. and you've got a huge pressure plate at the back, and you throw a bomb behind, it explodes in all directions, and you capture a piece of it, and it transfers momentum to the vehicle and pushes it along. So this was Project Orion. But for various reasons, it was controversial. There's a famous paper I mentioned earlier, 1968, Interstellar Transport, by Freeman Dyson. And that's where he actually did the economic extrapolation as well, 2% GDP per year, when you can actually build one of these things. And he estimated it would be around 2268 is when something like this was possible. But actually, in terms of economically, that is. But actually, in terms of technology, we could build this today. We could have built this decades ago. We know. So if we had an immediate threat out there in the universe tomorrow, if we knew there was an asteroid coming towards us, there's nothing we can do to thwart it, and we needed to get off world. Let's hope that never happens. That's a doomsday scenario. But in principle, we could build this. We know how to do it. It doesn't involve any new physics. But it is limited in its performance. So you've probably heard of atom bombs and hydrogen bombs. Hydrogen bombs involve fusion, like in the sun. So an atom bomb will get you to about 5% of the speed of light for powering this thing. And the hydrogen version will get you to about 10% of the speed of light. So you can't get much faster than that. So the quickest journey, you're looking at 130 years or so to get to the nearest stars. So you're still multi-generational. So people will still die on board the starship, and people will be born on the starship. So here is actually an illustration from Alan Bond in 1973. Some of you guys might have seen this before. Alan wrote a wonderful article in Spaceflight magazine where he looked at all of the options. This is pre-Daedalus. And this is actually an Orion. And you can see here from the nomenclature, A is the bomb chamber. So look at this as a stage system. So that's a bomb chamber there. And then you've got B as the bomb store. So they're stored here, just in here, sorry. And these are the shock absorbers. And this is what we call units going off and exploding. And this is multi-stage. There's 1, 2, 3 stages and a payload on the front. So notice that this is leading up to Project Daedalus, which is a 2-stage fusion system, because what Alan realized was that actually there's another way to do this. Instead of using bombs, we can just use fusion energy. And he realized that from papers of Friedrich Winterberg. Those guys published another paper in 1979, which is a really detailed study of this kind of propulsion technology. Here's a painting by Rick Sternbach, which was made for Cosmos. Whoever hasn't seen the Cosmos 13-episode series with Carl Sagan, please watch it. It's really cool. This was made by Rick Sternbach for Carl Sagan. I actually own the paintings and the drawings. I'm going to show all of them today. I've occasionally brought them in to show people, but they're really amazing drawings. And you can see here the shock absorbers, the pressure plate, something going off. I would love to be able to paint to that level. Really, really talented artist. This is one of the drawings that he did, and these were shown in the documentary when Carl Sagan went to Italy. He was showing these drawings in the film. If you go onto YouTube later and Google episode 8 Cosmos, Carl Sagan, you'll see all these pictures. So this is the Orion, you can see. So the idea was to illustrate in the future we can design starships. In 1960, we then had pretty much what was considered at the time a revolution in spaceflight, which is the idea of, the problem with spacecraft is if you have to carry fuel, the mass is huge, and that creates a mass ratio problem. So can we actually not have to carry the fuel and mine the fuel en route? So this is called an Interstellar Ramjet. So in space, there's lots of hydrogen in particular, which is protons. And the idea is use this huge magnetic scoop like a vacuum cleaner, and it pulls in all the interstellar hydrogens into a fusion chamber and then exhausts them out the back for thrust generation. This was published in 1960 by Robert Bussard, also a physicist. And these physicists do strange things, as you can see. It was an enormous vehicle, potentially, but on paper it has the potential to go relativistic. It was close to the speed of light. Remember, the speed of light is around 300,000 kilometers per second. Einstein told us it's the fastest law, the fastest thing in the universe. So it's the only technology we know that could potentially get us close to it. But there are some issues with it, which I'll discuss. This is another one of the Rick Sternbach paintings. And one of the issues is that protons, hydrogen itself, has a very small cross-section. In order to capture it and pass it for a fusion reactor, it's very difficult. That's why when we look at the laboratories on Earth, we tend not to look at just hydrogen. We look at hydrogen isotopes like deuterium and tritium because they have a larger cross-section. So it's easier to try and make them fuse. So that was one of the problems. The second problem is all of this hydrogen potentially is coming into this funnel, and it's building up and it's heating up the system. And it's almost like you're trying to eat too much too soon. And because you're going so fast, maybe 99.9% of the speed of light through the interstellar medium, the interstellar medium actually becomes like a drag force. And calculations by Bob Zubin Dana Andrews, actually calculated that it may actually offset, the drag may be so large that it offsets the acceleration. So people thought maybe this isn't possible. But there has been spin-off ideas, something called basically using the CNO cycle, carbon, nitrogen, oxygen cycle, which is done in the sun as well, to impact protons into carbon-12, and then you produce helium through that, because helium is what you're after in the fusion reactor. Another idea is to take protons with neon, and you can also produce helium. So these are some of the ideas people have looked at: Daniel Whitmore, Alan Bond, looking at the idea of actually having propellant on board as well, and augmenting that with some of the thrust generation from the particles coming into the stream. So you have two things happening at once. But the general consensus at the moment is the Interstellar Ramjet looks very problematic, but there's only been about 12 papers ever published on it in history. So I think we're at a very early stage. This is the drawing of the Interstellar Ramjet, again from Rick Sternbach from the Cosmos documentary. Now Carl Sagan, he wrote a wonderful paper in 1963, direct contact among galactic civilizations by relativistic interstellar spaceflight, and he used the equations of relativity from Albert Einstein, special relativity, and applied it to something like an interstellar ramjet, and actually worked out you could actually get to the center of our galaxy in only 28 years. Okay, using this technology, you could get to the Andromeda galaxy in 32 years. You could get to the edge of the known universe in 40 years using this technology. What's the problem with that, though? Can anyone tell me? Time dilation, okay? So Einstein taught us that if you accelerate fast through space, clocks slow down, okay? So for the observers on Earth, you've gone off on your journey to the center of the galaxy in only 28 years. But for them, maybe 1 million years has passed, okay? So if you came home, who are you? You know, in fact, they may have evolved. The human beings are completely different. They don't even know who you are. So this is the penalty to starflight. We may be able to get close to the speed of light, but there's a cost, okay? Which is you can't tell anyone you did it, other than the people in the future that you might meet. So there was another parallel stream of thought in terms of sending people to the stars, which is Ensman. We actually had communication with Ensman. He claims he came up with this idea in 1947. I'm not so sure. I think probably 67. He sent us a painting that he had done, and we published that in a paper we wrote in 2012. But this is using huge balls of deuterium. And the idea is you go off to the gas giants, you mine the gas giants for fuel, and then you then go off the nearest journey at 9% of the speed of light to the nearest stars. It starts off with about 200 people on board. At the end of the journey is maybe 2,000. So there's a lot of babies being born on this ship. So it's a very good idea, but no one really designed it. Some of the artists like Rick Sternbach and others did some work on it. But it is essentially what's called an internal nuclear pulse system. Daedalus, which we're going to talk about in a minute, is a hybrid because it's half internal, external. Orion was external nuclear pulse. This is an internal because the detonations are going off inside the spacecraft. Gosh knows what the vibrations on that would be. But it'd be an interesting thing to be on. So then we come up to what I call the golden age. So there was all this preliminary work done on thinking about starships and interstellar flight. There's so much I haven't touched on, astronomy, the SETI and so forth, but I'm trying to focus on the propulsion a little bit. I call this the golden age from 73 to 1991. In particular, the JBIS red covers, 74 to 1991, edited by Tony Martin, are just brilliant issues. I really admire them. When I was editor of JBIS, I tried to bring some of the red covers back, and they are still continuing today. In fact, we just had one out last month. These guys tried to put together a biography, Robert Ford and Malov. That's continued ever since. But this is where we had Daedalus start to arrive. So this is the one I was talking about at the beginning. This is the British Interplanetary Society design. And you can see the two-stage I was talking about earlier. So there's the first stage. There's the engine, big nozzle at the back. These are the propellant tanks. And the particles are electromagnetically accelerated. So inside these propellant tanks will be tiny little spheres, 1 centimetre and 2 centimetre in size, of deuterium and helium-3. And they'll be used. And then the idea is there's lots of electron beams around the outside. And all those electron beams will fire on the target and detonate and implode it to a thermonuclear condition. That's the idea. So this will accelerate for 2 years, and then this will be thrown away, and this will accelerate for another 2 years or so. And then this was an artificial intelligence probe with a particle shield at the front, 9 millimeters of beryllium, and that will get you to Barnard Star in around 50 years. So this illustration just shows you what's happened with the pellets. So you've got the laser beams hitting it. This is a thermonuclear fuel. It gets compressed up to high density and then it detonates. So it's like a little miniature explosion. And really what promoted them to push for Daedalus was the papers by Winterberg in 1973 when they realized that this could be possible. So what I'm going to show you now, and I'm going to rush through these because to try and catch up with some of the time we lost, it's just a load of illustrations, because what's happened is artists all over the world have been moved by Daedalus and its beauty, and they tried to capture it. So these are some of the original drawings from the Daedalus project. As I say, they did all the calculations for it. It was a really beautiful study. And these are some of the drawings, again, from the original project. And you can see the propellant storage particles are electromagnetically accelerated into the target chamber. The lasers hit it, and that's how the thing pushes forward. There's an illustration from a book. I didn't have time to put all the references for all of these, but I've got all these books at home. I had make it my business to track down any books which cover anything to do with interstellar in history, including children's books, because some of those are the best. This was from a children's book, a children's encyclopedia. You seen this one before, Jerry?
Somewhere, I can't
Yeah.
remember where actually.
And you can see up here, this is one of the sub-probes. So the little holes up here, there's actually, I think it was 18, was it, Terry?
Yeah.
18 sub-probes propelled by nuclear electric ion engines, and they'll be positioned in the top. The idea is you get to the system and you release those at the Barnard star, and they go off and explore the planets. The problem is you're still moving at 12% of the speed of light, which is how fast this thing was moving. So they're also moving at that speed, unless you can find a way to slow them down. So your science potential is limited, and this is a very large machine. More illustrations from the books. So here's some. This is a picture from the probe arriving at its target system. Remember, this would be artificial intelligence. You've got to remember, this is 1973 to 1977. This is really before the era of microelectronics. So back then, they were talking about vacuum tube technology. Okay, so when they designed this, that was what they were thinking about. That's when before microelectronics, but before the internet took off. You know, this is one of my favourite ones.
Actually, the team knew that it would all be superseded. It was just to show that it could be done. So
Yeah.
they would not argue that it could not be done. I
Yeah.
think even at the time, Kelvin knew that it was.
Yeah, so I should.
Right,
Yeah, that's good. So I should point out that actually the motivation for doing Daedalus wasn't necessarily just let's have fun and try and design a starship. They were interested in what's called the Fermi Paradox. Everyone heard of that? You know, if you look at the galaxy, how many stars there are, now we know there's lots of exoplanets, how the age of the universe and everything, you know, it should be intelligent life everywhere. And unless you believe, you know, that the flying saucers are real, that's the distinction. But you talk with a lot of physicists, they might not agree with that. But what they would say is that Fermi, who was a physicist at the time, in the 1950s, argued that we don't see any evidence of alien life, and yet everything we know about biology and physics tells us that it should be all over the universe. So that's a contradiction. That's called the Fermi Paradox. So one of the possible explanations for that was, well, nobody could build a machine to travel between the stars. It's just too difficult. No one can actually build a starship. Well, that's why they did this. And they concluded at the end of the study, they could, on paper, design a starship, in principle. Therefore, if you could do that at the outset of the space age in 1970s, what could you do in centuries from now? So, therefore, interstellar travel was possible. So that's not the answer. So it's something else. Okay. So I'll just show you these pictures. They're rather beautiful. Lots of illustrations of Daedalus that people have done. Joe Berger one. I managed to get the credit on that one. I apologise to the other artists if I haven't properly credited them. Nick Stevens. Some of these are done on a computer and some of them are hand paintings. I prefer hand paintings myself. This was Don Davis, I remember that one. That's a beautiful hand painting. Astonishing piece of work. This is David Hardy, one of our own, who also painted that picture on the wall over there. Can't remember who painted that one. I think that was a Japanese artist actually. This is Adrian Mann. This was done on a computer, but really cool. One of the things about this engine is it's so energetic, you couldn't actually launch it from Earth orbit, because it would just, if you looked at it, you'd be blind. It was so luminous. It's like looking at a sun's exploding. This is one of the other ones, again, from Rick Sternbach for the Cosmos series, which I have. Beautiful painting. I love the way he's done the propellant tanks. And there's Daedalus here. So as I said, at the end, make sure you go and see the Daedalus model, which is in there, and the artist who built it, Terry, at the back. Artist stroke engineer, because he's also an engineer. This is painted by Adrian Mann. Jerry, you might not have seen this one before. I commissioned Adrian Mann to paint this for me. And it's Daedalus staging. It's done accurately. So there's only two tanks left on when it actually separates. So you can see the second stage starts to light up. And what I actually did was I asked him to add something else onto it to portray an intelligent spaceship in the distance that's watching on as humanity first breaks out into the universe. Hence the dodecahedron. That's meant to be some construct, mathematical construct of an artificial probe that's watching our first attempts to get out there. There's another painting I commissioned from David Hardy based on a short story I wrote called A Dance of Angels, and it features a Daedalus-like spacecraft and an Orion spacecraft that are on a race together. And if you want to read that, it's published in Visionary 1, which is on sale on the BIS website, and it's got a bit of a Shakespearean theme to it. But essentially they're going off towards the stars together, but what I did is I mapped female attributes onto Daedalus, which I called Cassandra in the story, and male attributes onto the aggressive Orion, which I called Gabriel, and they're sort of competing, and they end up falling in love because they're artificial intelligence probes. So it's a really cool story, but something happens. And anyway, this is Sid Mead, who passed away just recently, and you can see the Ensman starship at the bottom and a Daedalus here. And another Ensman. So really amazing, the amount of work that's been done, inspired by these people. And here we have the models. So we've got, as mentioned, Terry at the back. That's the model which is sitting over there, which Terry took 5 or 6 years to build.
Yeah, about 6 years.
Okay, so there's been other models built. The first is the one by Matt Irvine, which was that was taken at Patrick Moore's house when I went there for filming on the Sky at night, and it was rather amusing because the propellant tanks kept falling off onto the floor, and Patrick was not amused. This is a model which is actually available on Shapeways website. It's a 3D printed model. It's very small. This is made in Indonesia. It's a wooden model. This one I've never seen, but a friend of mine went to a Star Wars exhibit. I think it might have been Alaska, and he took a photograph of it. And it was 1 meter tall. So it was built probably by the Hollywood kind of studios, and so there's only those models that I'm aware of. Wouldn't it be great if someone actually built a prototype one day? So once you get away from the flyby probes like Daedalus, you then think, well, could we send people to the stars? Because everything I showed you was uncrewed, okay? So this is the same guy as Alan Bond and Tony Martin started to turn their attention to world ships. This is an enormous world ship. It's got a pusher plate at the front again. This thing is about 200 kilometers length, to give you an idea of the scale of it, okay? It's 20 kilometers across. And this thing here is an oceanarium. So it's rotating, and you can actually go for swims, like a little ocean inside of it. So essentially this is a world ship. Everything you can think about what we do on the Earth, if you're going to build a starship and send people, you have to do that in space. The idea that you're going to send people on a long journey, potentially over decades, and it's going to be like the ISS, with noisy pumps everywhere, and you know, I remember speaking to Helen Sharman about this, and she said when she was up there, it was like 95 decibels, the noise level. When with the ISS, they got it down to about 65 decibels, I think. But it's very noisy, and you have to keep resupplying it. It can't be that way. You have to have it just like on the Earth. You need to be able to go for a walk, have exercise. Psychologically, you need that environment. So they started to look at designing world ships. We've also started to look at other, I say we, I mean humanity, so I'm sort of trying to paint a picture as humanity and our journey towards addressing this interstellar problem. So antimatter is the idea that, mentioned Sanger at the beginning, talked about anti-electrons, but actually later on we discovered that anti-protons also exist. And so if you can actually get anti-protons to collide with a proton, what happens is you produce a lot of pions. And pions are little particles which have charge. The neutral ones you can't do much with. They decay rapidly in like attoseconds. The charged ones, of which there's sort of 1.5 negative, 1.5 positive charge, they last for about 26 nanoseconds, which sounds very quick. A nanosecond is 10 to the minus 9 seconds. That's really quick. But actually, in terms of nuclear processes, that's something we think about all the time. But in theory, you could capture that and direct it for thrust. So people have looked at those sorts of ideas of using antimatter. Antimatter, remember I showed you at the beginning, is much more energetic than fusion. In fact, antimatter is 1,000 times more energetic than fission, 100 times more energetic than fusion. So if we could do antimatter, that would really make getting to the stars possible. But there's lots of reasons that becomes difficult. Some people decided, well, can we do it without fuel altogether? Is there a way to do it? Now, you've probably heard of solar cells. This is the idea of taking a big reflective surface into space, using solar light to push it through solar pressure. And what you need is a reflective material, large surface area to collect as many photons as you can. And in theory, you can be pushed. The problem is that the light of the sun falls off 1 over distance squared, the same with its gravity. So when you get out to sort of the gas giants, it's felt to such a low pressure that you're not really getting much push. It's only really useful close into the solar system. Unless you get your solar cell really close to the sun first, and then you unveil it, you can give it a really good push at the beginning. But it's great for interplanetary, but not for interstellar. And then we start to look at, well, could we use a laser beam instead of the sun? So we create our own sun. So 1980s, Bob Forward was one of the pioneers in this, followed by his student, Jeff Landis, who works at NASA, who followed in his footsteps. They started to look at concepts for using laser beams to send sounds to the stars. So this is a laser. I'll get this to work. And this is your spacecraft. It's a reflective surface, and maybe in the center of it is a small probe. And the idea is you need something called a huge Fresnel lens, which reconverges the beam. Because if you point a laser, you've probably gone out at night time and at the stars and pointed a torch up to the sky. Anyone ever done that? And you see what happens to the beam, it diverges, right? So that's what happens to laser beams, they tend to diverge. So when that's happening, if you're using that pressure for spacecraft, that's bad because the pressure's dropping off. And at some point, the pressure's just not there anymore. So you want to try and recollimate that beam. You want to redirect it, reconverge it. So that's why you need these lenses. So Bob Ford did all these studies, and he looked at flybys and actually full rendezvous, in other words, orbital insertion into the local star system. This thing's not working very well. And then also return stage, the idea of returning something back. Now, he gave a presentation to the US Congress in 1976, I think, on this topic, and they said, well, when's it going to be ready? When can we do this? And he said, about the year 2000. So he was a little bit optimistic. But this technology is, in principle, practical. There's been other ideas, and now I'm trying to go in time, but there's a later paper here in 2010, but this one, 1980, Frodian started to talk about quantum vacuum. So if you go into space and you have a cubic meter of space and you moved everything from it, all the particles, all the dust, all the electromagnetic fields, you think it should be empty, there should be nothing else there left. Well, actually, it's been discovered in physics that there's something called the quantum vacuum, and it's possible we can mine that to actually propel a vehicle. The problem is we don't know how to calculate rigorously how much energy there is in the quantum vacuum. There's various methods of doing it, and they contradict massively. So we're not quite sure how much energy there is. And this was used as the basis of the story, The Songs of Distant Earth, by Arthur C. Clarke, which is another story I'd really recommend reading. And this is an illustration by Philip Boucher, an artist, on what that quantum ramjet might look like. And then we get into wormhole physics. Okay, so in the 1980s, we had this film Contact. Yeah, all heard of Contact? Have you ever seen it? So you've probably all seen the Interstellar, which is also involves some of the same people like Kip Thorne advising it. Contact was a great film based on the novel by Carl Sagan. And this is the idea of using wormhole physics to actually take a shortcut in space. So in 1980s, some of the few equations I'm going to show you, I do apologize, okay, just so you've seen it. Actually, the origins of wormhole physics go back to the 1930s. Would you guess it? Albert Einstein. Okay, so Albert Einstein, when he was developing general relativity, he published that, but he didn't like the emerging quantum mechanics. He had several objections about quantum mechanics. And he decided to write his own, what's called a field theory, general relativistic field theory, of just like two particles, two electrons. And he wrote an equation for that, and this equation here is called the Einstein-Rosen Bridge. It's actually something called the Schwarzschild metric for black holes, or spherically gravitating mass you use for gravitating mass systems. And you do something called a coordinate transformation, a little mathematical trick. And you get this, and it basically describes a non-traversable, but essentially the mathematics of a wormhole. And that was the first real equation that was set down. And then you had others in the 1980s, particularly those that worked with Carl Sagan on Cosmos, Kip Thorne, who did some of the initial calculations in the back of a taxi, and he worked out some equations to describe this. So a wormhole, of course, involves a shortcut between 2 points in space without traversing the same linear distance. And there's reasons to think that microscopically they may be possible at the quantum level, work done by John Wheeler in particular. But we have no evidence that you could produce them macroscopically. But it would solve a lot of problems if we could do it. This is what a spacecraft might look like, traversing through a wormhole, from the artist Alexandre Zams. So now we come up to, so we build in the field. You see at the beginning it was all kind of science fiction ideas, people publishing the occasional paper, and then you started to get into projects. Now what I call the consolidation age, 1991 to 2019. So at this time, we then started to have some of the space agencies and others started to think about, well, we did the Voyagers in the 1970s, and it's about time we started to revisit that. So they came up with a mission called TAU, 1,000 Astronomical Unit Mission, which means go to 1,000 astronomical units. And it was led particularly by scientists at Jet Propulsion Laboratory in Pasadena. Unfortunately, it never happened. But there is a revisit of that project today, and I'll get to that. But meanwhile, Miguel Alcubierre, who's a general relativity postgraduate at Cardiff University at the time, he was a fan of Star Trek, and he decided to see whether the technology of Star Trek could be written down in paper, at least in principle. And I don't show it here, but there's a similar equation, they're called metrics, which is for something that how you would distort space and time. So the idea is you would have a ship, and you create a bubble around it. And the ship essentially doesn't move. So the ship's on a flat space-time. In Einstein physics, we call it space-time rather than just space, because space and time are connected. So you've got space-time here. It's in a bubble. Imagine it's like in a bubble. And then what you do is you cause the universe in front to collapse, just like in a black hole, space collapses, and the universe behind you expands, just like the universe expanded at the beginning of time, the Big Bang. So, because Einstein said that nothing with mass can go faster than the speed of light, but it doesn't prevent space itself from going faster than the speed of light. And that's what we think happened in the Big Bang, superluminal inflation. Superluminal means faster than the speed of light, effectively. So on paper, it looks great, okay? But there's lots of problems with it. So we did a symposium here in 2007. That was my entrance to this field. And then we worked on a documentary the year after. And I tried to design a warp drive system that broke as few laws of physics as possible. It still broke many. One of the main issues is once you create that bubble around the vehicle, it's causally disconnected from the surrounding space-time. In other words, it can no longer start and stop itself. So essentially what you do is you have this thing called a Casimir ring. Casimir energy is the only way we know we can get negative energy, which is what you need to distort space for both wormholes and for warp drives. You have this thing called a Casimir ring, which is gigantic, it's a megastructure, and you fire all these kind of lasers into the center, which creates this Casimir effect, which forms this bubble. So this is all speculative. And then you form your bubble, and then it accelerates it. So there's a whole ring of these, and this accelerates it up to the superluminal velocities you want to achieve. And the idea is that at the other end of the universe, there's another set of rings, or wherever you're going to, which decelerates it. So that's what we tried to do. But it's completely non-plausible, and it breaks so many laws of physics, even still. But it's fun to think about, okay? So NASA started to get interested in these ideas of breakthrough propulsion physics. In other words, they had three particular goals. Mass, can we produce concepts which drastically reduce or eliminate propellant mass? Speed, can we achieve the ultimate transit speed to dramatically reduce travel time? Obviously, if we could achieve the speed of light, it would be great. The speed of light is not like the speed of sound. Speed of sound broke it in 1947. Chuck Yeager, 14th of October, I think it was. That's a very different concept. That's an actual medium you're passing through. Speed of light is not a barrier in the same way. It's a fundamental restriction on how fast you can travel in the universe. And energy, discovering new modes of energy production. So Mark Millis in particular, who founded the Tau Zero Foundation later, he pioneered some of this work, really good work. We did the warp drive stuff, and then in this room we kind of decided we needed to try and revisit Daedalus, because Daedalus was in the 1970s. So we launched a project called Project Icarus. This was some of us here in 2009. This is some of the Icarus team on the right. We look like the mob. And this is some of the Daedalus team. Jerry's right at the front. And Alan and Bob at the back vying for attention. Bob's past president of the society. Alan's one of the founders of Daedalus. And it was great, and we had this idea. And Project Icarus, so we launched in 2009. Daedalus was a 5-year project. It's now 2020. We're still going. Okay, at our peak, we got to 100 people involved in the project through our organisation, Icarus Interstellar, and it dropped down. Now I can say there's about 6 people involved in the project. We're trying to finish it. And I'll show you some of the designs of that today. So when we reviewed Daedalus, we found lots of problems. Some of them were known to the Daedalus team when they reviewed it in the 1980s, such as Barnard's star. They thought there was good evidence for dust rings and an exoplanetary system. We then thought that wasn't the case. However, that's now changed, because now we think actually there could be evidence of exoplanets in Barnard's star. It's interesting. I talked about AI versus pre-microelectronics, helium-free mining. There's a whole load of issues. Pulse frequency, that's how many of these you're detonating per second. So each of these is going off like little bombs going off inside the target chamber, 250 a second. And that would generate a lot of heat load on the whole system, which really becomes a fatigue issue from materials point of view. They chose deuterium and helium-free because they thought they wanted to minimize the neutrons. Actually, some analysis, I haven't got this paper, by Hyde, later on realized that if you take some of the DD self-burn reactions from that, deuterium to deuterium, that will produce helium-free and neutrons anyway, eventually, by DT. So that was a problem. And there's lots of X-rays that were produced. So there's lots of issues with the Daedalus design we've been trying to address. We set about specifying our requirements for the project. We decided that Daedalus was only flyby, and we decided that we needed to decelerate. We didn't think it was justified to build just a flyby probe, given the likely cost that was involved and the amount of effort. If you're going to go that far, you might as well try and decelerate. So that was one of our requirements, and instead of 50 years, we decided to ease the engineering a little bit and try and do it in 100, because we thought that was technologically feasible. So this is some of us in Orlando in 2011, when we founded our organization at the time. A few names there, such as Stephen Baxter, science fiction author, who was with us, Jim Benford. A lot of the original guys. Jim French back here actually worked on the descent engines for Apollo 11, would you believe? He's still around. So we went to Orlando. We was involved with Untitled Starship. We were the co-winners of that competition. Didn't quite work out for us. I won't say any more about that. What we basically started off with is, in an ideal world, we produce lots of designs, but we have limited resources, limited time, limited people. So what I call inappropriate design scoping is when you say only produce 4 designs, but they're very similar. So it doesn't give you a really good idea about fusion. So we're trying to work out, what does it take to get to the stars using fusion engines, and how does that compare to Daedalus? So what we wanted is lots of different fusion engines, but with very different designs, and maybe we'd end up selecting one of them as the best one. In the end, what's happened, we ended up with about 5 designs, and probably about 3 of them started to move forward as being credible, and we're still working on them. We looked at flyby, we looked at precursor missions, so Icarus Pathfinder, Icarus Starfinder. These are some of the designs we did and published on. This one gets you out to the Kuiper Belt, this one gets you well into the Oort cloud. So these are like technologies you would build on the way to building something like a Daedalus. This is these concepts on the cover of Spaceflight magazine. Robert Freeland, who's a really brilliant engineer in the team, him and Michel Lamontagne designed this wonderful concept called Firefly. It's one of the options we came up with, and it's been published in JBIS quite a lot. And it uses something called a Z-pinch propulsion. A Z-pinch is a particular effect in physics where if you pass a current down a wire, you essentially cause it to collapse in on itself, it compresses. And this is a Z-pinch driven system. I didn't work on that, so I won't say much more about it, except that these massive things are radiators, because you've got powerful nuclear reactors, powerful fusion reactions occurring, that's producing heat. So you've got to get rid of that heat. Otherwise it just blows the spaceship up, right? It heats it up. So some of it, ideally you'd like all of it to come out the back, but there's inefficiencies and there's conversions. So the first one I started working on was something called Leviathan. That was published in Space Chronicles, but these graphics were done later. And Leviathan was a very complex design involving deuterium helium-3, deuterium proton boron. It involved about 4 different deceleration mechanisms, and this would go out off to the stars in sort of 100 years and achieve the mission. But the team thought this was a bit complicated, maybe we need to simplify it. So I moved to something else. These big things are radiators, by the way, again, trying to get rid of all that heat. I moved to something called Resolution. This is essentially the Icarus second stage, but with more propellant tanks, and it essentially turns around and decelerates itself. And we demonstrated that this was possible, that you could just use the second stage. It has about 20,000 tons of deuterium helium-3 fuel. It takes the 100 years to get there, but it decelerates. It turns around, fires the engine the other way, completely decelerates into the system, and then you can deploy your robotic landers, whatever. But the problem with that system is the burn time for that, in terms of how long the engine was firing, was 15 years, which we thought was too long. We thought that would create lots of engineering problems, and we needed to cut that down. So we moved to a 5-engine system, which is called Endeavour. So the people working on this was myself, Rob Swinney, Richard Osborne. Richard Osborne's particularly been working on the power systems and some of the other areas. So this is the Endeavour, and you can see it's got 5 engines, so it's a bit like the Saturn V, the Quintec engine system. That's where I got the idea to do it. Visiting one of the Saturn Vs in the United States and seeing the engine, and I thought maybe we could paralyse the thrust. So that's what that might look like. That takes only 3 years to get there, to accelerate up to the required velocity, and then it cruises over sort of 90 years. And now we've moved to something called Pegasus. No one's ever seen this before outside the team. It's only been seen in the team. So this is brand new, and we're calculating this at the moment. The problem with the 5-engine system is you're still producing a lot of neutrons, a lot of X-rays, and this heats the structure up. So what we decided is to get rid of that central one, move to 4 engine bells, and put radiators around it. And what we're also doing is using a very clever capsule design, which captures a lot of those X-rays and absorbs the neutrons from the reactions. And you well insulate the the target chambers as well. So this is Pegasus. This is the current design which we're working on, and this is our team's successor to Project Daedalus, as well as the Firefly. Those are probably the two most advanced designs now that we have. We're hoping to publish that by the end of the year and get the project finished. So we're still working on it. And what actually happens is because it's got 4 engines, is some of it separates. So it goes to like Alpha Centauri, but of course you've got Centauri A, Centauri B, and you've got Proxima, and there's 3 stars near each other. So the idea is you could fly some off and they separate, and so you could explore the whole system. So that's why you've got this one with 1 engine on the back. This is a flyby stage, and it just accelerates off and explores maybe one of the other ones. So other designs we've worked on. How are we going? Were you all keeping up? Yeah, I'm sorry if we've gone at a fast pace. I've been trying to catch up with the loss of time. This is another design I worked on, which I never published it, but it's actually a black hole engine, would you believe? Okay, so this is now what's really interesting is this image has been used in a lot of magazines and websites, people's papers, and they just call it black, but no one's ever explained what it is because it's my image. I created it with Adrian Mann, and what they don't realize is that this is the CERN particle collider. Okay, so if anyone's watching on YouTube, whatever, they now know that for the first time because they've never actually read the paper. This is a particle collider. So the problem with the Interstellar Ramjet is you've got this very small cross-section of hydrogen, okay? So my idea was, well, at the time when they were building the circular collider in CERN, there was concerns that if you accelerate 2 7 tera-electron-volt protons together, and if the assumptions of multiple dimensions is true, like string theory, where there might be more than 3 spatial dimensions wrapped up at a quantum level, if that was true, then it would change something what's called the Planck length. The Planck length is given by 2 numbers, the gravitational constant g, speed of light c, and h bar, which is the quantum uncertainty, Heisenberg uncertainty number. So what happens is it changes the effective gravitational constant, and this changes something called the gravitational radius for collapse. So if you remember your black hole physics, right, you all remember it. So if you could take a star has to be at least 3 times the mass of the sun, something called the Chandra-Shekar limit. You have to 3 times the mass of the sun, and it gets to the point where it collapses, and it collapses so densely that it goes inside of its own event horizon. So if you were inside of it and you were shining a torch, the light couldn't escape because the escape velocity is too high, okay? That's how you get a black hole. It has to be a very massive star. In order to make our sun become a black hole, you'd have to shrink it down to about 3 kilometers. In order to make the Earth a black hole, you'd have to shrink it down to about 2 centimeters. So black hole physics is, everyone's familiar with Stephen Hawking and others who worked on this stuff. So the idea was to actually, if it was true that there were more than spatial dimensions, then it would change what's called the Schwarzschild radius for gravitational collapse. In other words, it wouldn't be 3 kilometers to collapse the sun, it would be something else, okay? So what I did is I did some calculations on collapsing 2 protons together in the interstellar medium, and they would collapse within the Schwarzschild radius. And what you then get is you get what's called Hawking evaporation, because they evaporate, they radiate inversely to the mass. So smaller the mass, the faster they radiate. This is what Stephen Hawking discovered. They produce a shower of particles, particularly leptons, which are charged. And in theory, you could use this for thrust generation. So I never actually published a paper, but what I did is I worked with a student at the International Space University, Andrew Alexander, and that was his MSc thesis for his degree. So I worked with him on that, and we never actually published a paper in a journal, but this was the concept. So it's a black hole engine, and it's my solution to the Interstellar Ramjet. So anyway, others have looked at black hole engines. So this is, anyone guess? Event Horizon. So I actually have a model of this, and I spent a few weeks ago trying to paint my model, which is an interesting thing to do. So this has a black hole engine. It's an artificial singularity. It's a really cool film, but it's a horror film, just to warn you. So, but it's a really cool film. But it's amazing the crossover between the art world, music, and the movie world, and real life physics. So we get to the end of our kind of propulsion journey, and we start to realize that there's been enormous effort by people to think about how we could build spacecraft to get to the stars. And this is a map. I won't go into describing it to save time today, but it pretty much shows you all of the methods we've ever came up with to get to the stars. From using some of those I've talked about, like the solar cells and the laser beams, to electric engines, nuclear fission, fusion, antimatter, and these are some of the exotic things like TARDIS time machine even, some of the ideas that, because people were actually working on that, would you believe? Some of the ideas people have come up with. In fact, I gave a talk, I'll show you the photograph at the end, to a school in Houston, 300 high school students. I'll show you that picture at the end. And at the end, all they wanted to ask me about was Harry Potter and Doctor Who. Just fascinating. So, fortunately, I knew what TARDIS stood for, which is time in relative dimensions in space. So I passed their test. So anyway, there's all these methods. I haven't got time to go into that today. And there's these eras that we've been through, where these founders that founded this field. I mentioned their names. And there's this golden age of these people, the Daedalus team and others, who pushed it even further forward. And there's all the others in the consolidation era. What's really interesting is this is also when the first exoplanet was discovered. After this, all of the effort really ramped up. And then you started to see the emergence of all these interstellar organizations. There's now about 7 or 8 organizations in the world who are non-profit, like in America, 501(c)(3)s, or charities in the UK, that are doing interstellar studies. Okay, so the BIS has been doing it since 1933 when it was founded. It really began looking at interstellar in the 1950s and 60s, but it's been doing this stuff for a long time. I'm probably going to have to skip over some of this because we haven't got much time. How are we doing for time?
Past it.
Okay, right, let's... right, so what I want you to think about is Leonardo da Vinci. So you all heard of him many centuries ago. You think of the concepts he was coming up with. They must have thought he was mad, right? So these parachutes, and aeroplanes, and helicopters, and yet today it's a part of our modern society. But some of this has been around for a long time, and so I like to think of starships in that context. They look like they're fantasy, and in fact, I've been called a fantasist and a dreamer by people that I admired. But and it surprised me because actually I think it's a lack of foresight for what's coming in the future. Here's an example. 2001, I mentioned at the beginning, this is the actual spacecraft from 2001 Space Odyssey. In the year 2001, NASA actually tried to redesign it. This is one of the first NASA studies looking at an actual spacecraft, goes to Saturn and back, uses a magnetic fusion engine with these huge radiators, but it's plausible. They haven't quite cracked the magnetic fusion bit yet, because that's still an ongoing experiment. But even NASA's starting to look at this stuff. What I want to tell you about, there's 3 professional projects that I've been involved with. So a lot of these other projects I mentioned were hobby kind of projects or things on the side. But there's 3 professional projects I've been involved with, which are involved directly with designing a starship. Okay, which just shows that it is really happening. And you've got to think that in the 1920s and 30s, all the rocket stuff was happening. And in the 1960s, we went to the moon. How quick that happened. So the question is, how quick is it going to happen when we start getting out into the stars? And I think you're at the beginning of that. You're going to see that. Maybe it might not be in our lifetime. It might be in our children's lifetime. But it's a very exciting time to be alive. So I worked on a study with the International Academy of Astronautics, 2008-2010, which is a mission to 200 AU. That's kind of like double the Voyagers. Okay, that was only a paper study. But it was published, and it took about 5 years for the paper to finally come out, but it was published in the end. I've been, for the last few years, 2017, 2019, working with Johns Hopkins Applied Physics Laboratory, and they've been trying to build up momentum behind a 1,000 AU mission, something that goes beyond the Voyagers all the way out to 1,000 AU. And that's moving along really successfully. This is us in New York at the Harvard Club of New York, and having our meetings. We've worked on other projects. Project Dragonfly is a laser sail project, Project Andromeda, and we use those to really help to convince the breakthrough initiatives that their project was credible, that they should launch it, and indeed that happened in 2016. This is Yuri Milner, who's a Silicon Valley billionaire, entrepreneur, who's also a physicist, a really great guy, and Stephen Hawking, I also got to meet Stephen Hawking, very privileged, and some of the others. Pete Warden, who's the lead of the project, announcing the launch of this project. And they announced $100 million behind it to start with, which is a pretty substantial amount of R&D money to fund this initiative, to actually try and design a starship using directed energy. So the 3 things that really made it plausible was the continued miniaturization of electronics, the possibility of materials at the nanoscale level, and then ideas from fiber optic communications that you could use that for example, making phased array lasers. So you bring lots of laser beams together to push. So the idea is that it's on the laser beams on the ground, and it pushes the starship out into space. So it's the Starship's in orbit. It's very small, about 4 meters in size as a SAO, and you fire the laser beams from Earth and it pushes it out into space. In principle, you could also do that in space. And that's an ongoing project, and that's been funded for the last few years, and that's making really good progress. And you know, the guy who runs Facebook is also involved in it, Mark Zuckerberg. He's also behind the project, so that's pretty cool. How much time have we got, Alistair?
About minus 10 minutes.
Right. To be fair, I lost 10 minutes. So. Okay, in that case, I'm going to have to skip over what I really wanted to talk about, which is the philosophy stuff. Well, the slides will be available. The slides will be available.
I'll tell you when to stop.
Okay, right. I will try and go through it as fast as I can. This is just roadmap stuff. It's about, we know roughly how to build a roadmap to go to the stars. 200 AU, 1000 EU out to interstellar missions. Okay, and this is just a diagram showing what a roadmap might look like. And this is coming out in the paper shortly. And Jabez actually wrote this in 2011. So I mentioned the Milky Way. You know, we live in this galaxy. This is actually an image of another galaxy, but the Milky Way kind of looks like that. No one's actually been outside the Milky Way and taken a picture. So anyway, so 100,000 light years across, and the idea is we could perhaps explore this. So what you could do is you could actually look at something called distribution functions, and you can plot for lots. So if you imagine there's a galaxy filled with civilizations, like 1 million civilizations in the galaxy, okay? Intelligent life forms, and they're all living throughout the galaxy. They've all got different spacecraft velocities. So some would have Daedalus-like machines traveling at 12% of the speed of light. Some would have world ships traveling at 1.5% of the speed of light. Some might have relativistic spacecraft. So the idea is there's this distribution of velocities with civilizations that hypothetically might exist, okay? And so if you had a galaxy where everyone only had world ships and no one had anything faster, that's what the distribution would look like. And if you had a galaxy where everyone only had Daedalus-like spacecraft, that's kind of what it looked like. The average would be around there. Well, what's really interesting is what happens is, I called it temporal spaghettification because of the time dilation problem. If everyone's got different velocities, how on earth do you arrange a meeting? Okay, so you're on different stars that started they're born at different points, different planets that evolved, life evolved at different rates, and a galaxy that's 10 billion years old, whatever, and you're all traveling at different velocities. And so the idea, like Isaac Asimov, that you'd have a galactic foundation where you have like an empire, or like in Star Wars, where you have some emperor that lives on some planet is ruling the galaxy. So non sequitur, it doesn't work because of time dilation. It just breaks down because as soon as you start accelerating, it changes the clock time. So I call this temporal spaghettification, and this makes the idea of a galactic civilization impractical. And if you start to one of the other things that happens if you start to if you get exposed to other civilizations, I mean, what happens with cultures on Earth? Like when the Aztecs met the Spanish, there's a transference of technology and ideas. Sometimes the lower culture ends up being decimated because of that interaction. But what happens is you exchange information. So if someone's got particularly cool technology, like someone had warp drive technology, eventually everyone's going to get it. So what happens is this distribution sort of starts to shift, and eventually you end up asymptoting towards what's called the speed of light, and you end up having what's called a runaway effect. I haven't got time to go into all of this, but basically there's reasons why I created something called a law, which is or a postulate, which is that you can't contain information indefinitely. The best information prison is a black hole, and even that leaks. Stephen Hawking showed that. So you can't contain information indefinitely. So you can try and keep something secret, but eventually it will get out. Even if it takes millions of years. So if there's a technology that exists like FTL, eventually everyone will have it. And that really makes the Fermi Paradox pretty difficult. I'm going to skip over some of this because I haven't got time to go over it, but you can watch the video back and see the slides. Presumably you'll get the slides from the BIS. So we know we can explore the local stars. Okay, that's pretty much given. What about the rest of the galaxy? And what about beyond the galaxy? Because there's billions of galaxies out there. I mean, a galaxy contains 200 to 400 billion stars, and there's billions of galaxies. I'm pretty confident in the future we're going to go off and do some amazing things, like building ring worlds and space elevators and Dyson spheres and even matryoshka If you haven't heard these words, look them up. A Dyson sphere is a huge spherical structure built around a star, and you trap all of the heat energy within it. So 100% of the energy from that sun is converted into useful work. And a matryoshka is like a huge brain, like an artificial intelligence you build around it. So you've got, imagine AI technology combined with a Dyson sphere. You've got like a godlike creature that lives around a star. These are things that we think may be possible in the future. But there's several things I'm concerned about. Probably another 5 minutes and then I'll be finished. Okay, so the things that I worry about is the constant speed of light. Okay, that's a problem. We can't go faster than the speed of light, and there's no evidence that we can. You know, space, we've got ideas for space moving faster than the speed of light, but those ideas break down when we look at them through physics and engineering. The size of the universe, we've got an idea what the size of the universe is, but it's unbelievably large for our needs. I mean, we just don't need a universe this big. And you could say, well, you know, maybe it's for everyone in the universe. Well, where is everyone in the universe? Because there's lots of evidence we can't see anyone in the universe. So why do we live in such an enormous universe? It's like it's so big that we can never get to explore all of it. Okay, so it's unnecessarily large for our needs. There's a time dilation issue, which is that if you want to discover the secrets of the universe and you want to cross the universe, to go to the center of the galaxy or to discover what the meaning of life is or whatever it is you're trying to find, like in Star Trek. The consequence is time dilation says, well, the consequence you can't tell anyone because you've gone so fast. You know, the clocks have changed. And then there's the uncertainty principle of quantum mechanics, which is if you try to look at things on a very small scale, like if you try to look, you know, you get electron microscopes, you look at things very, very small. If you try and measure a particle, the uncertainty principle places restrictions on how much accuracy you can give to the position and the time, or the energy and the time. Well, what you have to do in order to see it more closely, you have to beam more energy in. The act of putting more energy in actually creates another particle. It's like the universe is playing games with us. It's like it's creating a mirage. It's like it's saying, oh, you're trying to look, are you trying to look under the hood of what the universe is made of? No, no, no. And it creates like another particle just to confuse you. And that's the probabilistic uncertainty cloud, right? So the universe seems to me, it's not letting us see outside, it's not letting us go across the rest of it. And I worry about that. And a way to represent that is, there's something in physics called the Bronstein cube, hypercube, which relates all of the ideas in physics like quantum gravity and so forth. And I see this like a prison. It's like we're in a toy prison, this universe, and it's made of these things like the gravitational constant, the speed of light, the scale of the universe. And it's like it's saying, look, your purpose in life is to be in this universe and to explore this universe and explore life, but it's not your function to go outside of it and ask what is outside the rest of it. It sounds like a anthropic kind of reasoning, and it is. But that's what I worry about. So I'm a big fan of some of the ancient stuff as I curve off towards the end. This is the Epic of Gilgamesh, which is one of my favorite books, written thousands of years ago. Just listen to this. What you seek, you shall never find. For when the gods made man, they kept immortality for themselves. Fill your belly day and night, make merry. Let days be full of joy. Love the child that holds your hand. Let your wife delight in your embrace. If he leaves alone are the concerns of man. And I wonder, Arthur C. Clarke's novel, Childhood's End, he has Carellin says exactly the same thing, the stars are not for man. Sorry for the women in the audience, I didn't write those words. So this is an image from a brilliant artist, Akian Kramaric, who I think is tremendous. She started painting when she was like 4 or 5 years old, of what a multiverse might look like. Okay, so is there other universes? Can we travel to them? What I wonder, if you look at things like the visitation phenomenon, the UFO phenomenon, there's people who believe in nuts and bolts technology, that there's flying saucers coming here. And there's others, such as Jacques Vallée, who's been writing books on this, a French Californian physicist for years, who argue that actually it may be something more deeper going on. Because you look throughout history, we've got these visitations throughout our history, going to witches and werewolves and dwarves and elves and goblins and so forth. And there's a feeling that actually, if you speak to some of the physicists working at the front edge of this stuff, if there's anything real to this phenomenon, it's actually more likely to be interdimensional than it is actually people coming from, say, another star or another galaxy and trying to land on our deserts or whatever and scare us with their flying saucers. It could be something much more profound that's going on like that. I actually think it may be something a bit even more different, which is related to altered states of consciousness, which gets into psychology. I won't go into that today, but here's an interesting thing you should be aware of from Carl Jung. He was ill, and in 1962 he wrote this book from an experience he had. It seemed to me that I was high up in space. Far below I saw the globe of the earth, bathed in a gloriously blue light. I saw the deep blue sea and the continents. Far below my feet lay Ceylon, and in the distance ahead of me in the subcontinent of India. My field of vision did not include the whole earth, but its global shape was plainly distinguishable, and its outline shone with a silvery gleam through that wonderful blue light. The sight of Earth from this height was the most glorious thing I had ever seen. This is in 1962, okay? So he claims he saw the Earth. He had a kind of vision, a lucid dream, he saw the Earth. And he said, your vision will become clear only when you can look into your own heart. Who looks outside dreams, who looks inside awakes. So I actually think the kind of meanings, the explanation of the deep questions of life is to be found in our consciousness, and understanding what consciousness is in our subconscious, and thinking about that. Although I continue to want to explore the stars. Last couple of slides, this is the photograph of me talking to all these American high school students. Fortunately, none of them's pulling funny faces, but it was a horrendous ordeal. 300 science magnet students that NASA hosted. There's this lovely quote at the top from Native Americans: we do not inherit the earth, we borrow it from our children. So I kind of want to paraphrase that a little bit. If we do not invest in the stars, we deny it from our children. I have a video for 5 minutes. There was an original video for this which has gone missing, and I found this alternative one from the Stephen Hawking documentary. What it shows is the construction and launch of a Starship in orbit. It's pretty good, apart from the fact that it's being launched in Earth orbit, which you probably don't want to do because it's energetic. But it's a really good couple of minutes film just to give you an idea of why I get excited about it. Maybe it's good being quiet, and I should be quiet myself. So they're just talking here about why we can't use rocket technology. It's just like 1 minute and then they go into the Starship. Remember, there's no sound in space anyway, so you wouldn't hear it.
What's the length of that ship, Kelvin?
If I was to guess, maybe 1 kilometre or 2. I've never seen an actual design for it, so I don't. But I just love the video. It's good. So maybe we'll carry on with the Q&A then, while we allow that to play in the background, because then we can catch up with a bit of time.
Okay.
So
Right, any more questions? Gone awfully quiet now, hasn't it, John? There we are.
Just a couple of observations, maybe sort of slightly top and tail what you said. There was a little bit before the first of the eras you described, and I'm sure you're aware of it, but a nod to Konstantin Tsiolkovsky, who suggested, at least sort of indirectly, that the laser push idea might work back in the 1920s. And I think, who was the Russian physicist who gave him the idea? Yeah, right.
Yep.
And then at the other end of what you were talking about, the whole question of the anthropic principle, and you know, why and how we fit into some sort of universe, and why the universe is the way it is, and why Planck's constant happens to be what it is, and why the devil are we here? So top and tail of what you said, really.
Yeah, so that's what we're all, I think, interested in those questions. Where do we come from? Why are we here? What's the purpose of life? And I think you get to a certain age in life, and these questions start to hit you more, particularly when you get to middle age. I think they hit you more. And it's like, oh, well, what am I doing here? You know. So my own physics quest has turned back to those sorts of questions, and I read a lot of spirituality and religious stuff as well. I'm currently reading a lot of Buddhism, Hinduism, a lot of Vedic and Sanskrit. So I'm interested in those ideas. And it's amazing, some of the cosmology from those earlier ideas. It's amazing. But yes, Fedorov and Konstantin Tsiolkovsky were the first to start to talk about the idea of going to the stars. I mean, Fedorov wanted to save all of humanity, including everyone who's ever died. He wanted to resurrect the dead. So he was really interested in life preservation for everybody. But they did talk about expanding often to the universe, but they didn't really go into great detail. Robert Goddard also looked at, I meant to say this at the beginning, Robert Goddard also looked at electric iron engines potentially in some of his papers in the 1920s. So he was one of the first people to write about that. But really, I think Sanger and Shepard were the first to really try to put things down in terms of numbers and try to really calculate an interstellar journey. I've not read the Sanger papers, but I've heard about his work quite a lot. But the Les Shepard, as I say, I only read his paper this morning, and it's a brilliant piece of work.
Right, yours?
Kelvin, when you started with Icarus, one of the statements you made way back then was, "We want to do it. You need to get there quick," and by that you were referring to a 5%, 10% speed of light, potential vehicle. You've mentioned today a broad spectrum of vehicles, some of which are very slow world ships, and others that can do a considerable fraction of the speed of light. One of the often cited reasons why you might want to get there quickly is because if your vehicle will take you a century to get from here to Barnard Star, Alpha Centauri, or wherever, it might only take more than a century, say it takes 500 years or something. You run extreme risk of, when you're arriving there, finding that 450 years before, you, as a machine launched a century later, overtook you. Do you still hold that view, or?
Yeah, so that's called the weight. That's something called the weight equation, which is, let's just wait till we've got faster technology. But if you wait, you'd never build and you never launch. So it's quite, how long do you wait? My answer was always just go with what you've got, because you don't know how long we've got to actually attempt. Anything could happen with the Earth or human civilization. I just want to see us get out there. Without a doubt, things like Daedalus and things like the Icarus will be seen as steam engines. I mean, they're ridiculous, really. And I'm sure that any realistic starship won't look anything like those when we actually come to building them. And we already know that from Breakthrough Starshot. These are tiny little Graham Scout wafers, which look nothing like, just like little silicon chips that we would have thought a starship or a spacecraft looks like. What I didn't say was that the Icarus designs tend to be around 5% of the speed of light. When I initially started Project Icarus, I was like, we're going to have reduced mass, we're going to have faster than Daedalus. I was like, we're going to beat them at everything. And as time went on, I started to think about it. I thought, actually, we want to go slower because we want to ease things a bit and ease the engineering technology. So, and also we wanted to do something which is credible in terms of future decades. So although these things are likely to be built, maybe a century or two from now, I actually believe the first starships were launched before the year 2100. That's been my claim for years, and I think the evidence is starting to support that, unless something really bad happens on Earth. But you want to really just get out there and make the attempt. Daedalus is 12% speed of light, Icarus is 5% the speed of light. That's plenty of time. 100 years is nothing in the blink of an eye of a civilization. We think how long we've been here. Since Sumerians, 3000 BC. It's quite a short time.
Anyone else? We're running out of time. Pubs close at some point. Right. I think that's it then. Oh yes, you've got a question. Well, we've got to get you in.
Yeah, just a quick question about antimatter drives. One thing I get slightly confused about, theoretically, matter-antimatter reactions completely change matter into energy. Mm-hmm. Okay, but matter doesn't have any mass. So but energy doesn't have any mass. So where does the reaction mass for the propulsion come from?
Well, it's just conservation of momentum. It's a lot of gamma rays coming out as well, which you can't do much with those. But it is the mass that you're interested in, the mass and the charge things. That's the conservation of momentum and conservation of energy. That's what you're trying to, I could show you on paper, but that's what you're trying to calculate. Essentially, when you look at nuclear fission, you're looking at something called the mass defect. That's the energy that comes out that produces the difference, that gives you that enormous amount of energy. It enables you to do extraordinary things. But it's like you're doing an accountancy problem, credit and debit. You can show through the equations that what comes out must equal what went in, but you can have a gain on it. That's the amplification of it, and that's what you're really trying to achieve.
Right, I think that's it. I think we've got to pack up now. Kelvin, thank you very much once again. Please thank him for an excellent talk.